I try to fill it up with content. I am an architect by profession, but I am working at the Department of Stability and Construction. I keep thinking about the same mechanism, stability, independently of what I have in my hand. Well, the title is quite interesting. It is from Fragments, Historic Monument, Supporting System, Construction, Sustainability. So this practically reflects my way of thinking. And the now the engineer in Hungarian was invented by Andras, and better if we have this. So what I'm speaking about little fragments, as a preface, I would like to tell you some ideas about monument protection, environment protection, and about what to do about it in my own profession. And then there is a little introduction where I would like to connect a historic monument and supporting system, and then this is my idea, how supporting systems behave. It will reflect our approach, and I will show you the different differences between the different systems. Monument protection, environment protection is very important in industry as well. By 2030, CO2 emissions should be decreased by 42%. There are different requirements. It is only to decrease it by 45%, but concerning the process, it means 10% per year. What can technology do about it? We should decrease the amount of material, and if the material is like that, we can decrease the amount containing CO2 should be decreased. For example, concrete. After 2030, we should implement new technologies, new materials, and new structures as well. Perhaps we don't have anything, any knowledge about it to be developed. And one statement is to build nothing. Yes, that's very environmentally friendly. It is connected with monument protection, to preserve the existing ones, to renew the existing ones, but preservation and renovation can be done in different ways. What can an engineer do about it? To use the least possible material. If there is old material, that should be reutilized. Effective structures should be used. They can be very different ones. The existing ones can be effective if we understand its behavior, and the new one can be effective if we create it in that way. It can be expressed as a slogan, right material to the right material. We don't have to use concrete and steel all the time. We can use different ones as well. And we should maximize the utilization of the material and of the structure. Only the most important one, and with minimal intervention, which can be so. These are the ideas which are in connection with environment consciousness, and they are of course, present in the word of monument protection. When we speak about the supporting system, not only the function, not only the shape, the form, the aesthetic style or architectural style can be considered to be of a monument, of a listed monument, but also the supporting system. So practically every part of it, the supporting system, the material, the technical features should be preserved, trying not to alter it. The biggest responsibility is the designer of the supporting system. There are different approaches that there have always been different approaches. There is an old interpretation and a modern one, which perhaps didn't speak about it, but the way they approached it, well, it was obvious that the structure was important. And then first we tried to use modern materials, but then we realized that they have negative impacts. For example, in Italy, a lot of buildings were renovated with concrete, iron-forced concrete due to earthquakes. But then it was realized that when another earthquake occurred, then the structure didn't work properly. Another system should have been used. It's very important to have research, pre-research, concerning the supporting system, how the material behaves, how the supporting system behaves. With the modern tools, modern stuff, we cannot really replace the old structures because the result may be quite negative. In Venice Charter, which was issued, well, they emphasized that the traditional historic material should be used, should be preserved. Minimal intervention is required. We know some ideas about the old supporting system. It can be developed. So, for example, when we had an approach in the 1960s, 70s. It was modern at that time, but due to technical and scientific development, it has changed. So now we should implement structures that and we should preserve the original structures, because later development may reveal that it was not unnecessary and we should go back to the original one. There is an international organization within ICOMOS. This is a committee which has recommendations, which is practical, which is desirable to examine supporting system. The modern calculation, modern standards are not really practical when examining the old traditional structures. We always have to examine that the supporting system of a historical monument, what condition it is and how it can be used in the future. So it would be very important to monitor such kind of a structure continuously, and we should make a decision what to do, what kind of alterations to do For example, in case of a building, first we just observe it, watch it, and we should have intervention just when it is necessary. It's a long process. An organization should be created which could have a professional approach. This committee says that a historic monument cannot be examined on its own, but a historical context should be taken into consideration. Cultural context, everyday use must be taken into consideration because it might be different from culture to culture. So when we think about the situation here in Central Europe, but when we go to another region, it can be very different. I cannot use the same approach in Asia, for example. Some little details about the recommendations. We should use original material morphology and supporting system. It is in Mosonmagyaróval Hamber barn. There were old ones which was eliminated, not with the original one. With wood, it would have changed the original appearance. We should respect and consider the structural and environmental quality of the original supporting system. The original concept, we should respect the original concept, original materials, original building technologies. Now we reconstruct from iron concrete the wall structures. Concerning the wall structures, we don't have a lot of experience. We have what experience we have. It is the negative aspects of iron concrete. A good example is this church in Dresden, where the new building was created from the old material. We should leave the original, we should keep the original supporting system, even if it is not very suitable. Perhaps it could be set back. And then deformations may have occurred in a historical building, which have become part of the or a typical feature of the building, and we shouldn't restore. We should it back to its original state. Some little examples about the approach, which is about how supporting systems appear in historical context, and which shouldn't be altered because they are just right for the original condition. One example is a ceiling, and the other one is this flying staircase, a very new one. It was created in 2014. They made a model, 1:10 proportion. It was built on scales, and And that's how he created. Well, there are, of course, computer systems, but they cannot be used because the behavior cannot be seen from cantilever staircase. It's a console staircase. It's not a console. Let's see first this kind of ceiling structure, iron beams placed which are connected to each other. And if one starts moving, it makes the other one move as well. It is usually rested on a beam. So in this way, the beams work together. But is it important? Does it have any importance? This supporting system designer is created one by one. So here we can find something which can be utilized in this case. For example, another example is 5 meter per 8 meter ceiling. And this figure shows that one beam, what kind of effect the other beams have on a single one. Well, we can see how many elements are. Well, if it is 5, then it would be very wide panels. So about 25-30 beams should be placed. That is desirable, 25-30 centimeters. And then we can see that if we take into consideration how the beams work together, but if we see that it is a square system, then the tension is 30-40% bigger. So this structure is very useful because in this way the beams are forced to work together. So it is like a sheet, one sheet panel. Here you can see the data, you can see the values. What happens if how it would work if it was just a single sheet, single panel. But it also shows that in case of this the ceiling structure, we could make use this effect. And in this way, the examination of such kind of ceiling structure, supporting structure, shows that this idea could be used in modern structures as well. So perhaps even if the load is bigger, it could work functionally. And this one is my favorite, this staircase structure. It first appeared in the book of Andrea Palladio in 1570, but Palladio refers to this structure like heritage from the Roman times. It got spread in England. It is fixed into the wall at one side, but otherwise they are connected to each other and they are resting on each other, prefabricated elements, and it's easy to mental. How is it possible to measure such kind of a system if we consider it as a console? Well, let's take it a console. Well, in very many cases, a steel beam was installed to make sure that the staircase could stand. In Vienna, they made experiments. But we take the steps, a load on it, and then it will work. A staircase was dismantled, and we asked the expert if it works or not. No, even if part of it was dismantled, but it was working on their own. And it's interesting that it was not broken at the wall, but it got broken finally in the middle. But how can it be how can it be built? There are different systems. We don't put anything underneath. Does it work in this way? I start the first one and put the other one, and then nothing supports it. It can be done, and then we can build it from a scaffolding, and then you can see that the material is very thin, which goes continuously all the way long. So if it was a steel construction, it would be a lot thicker, but in this way you cannot. You can see it is only 5 centimeters, and we don't need any more. We can create a static model that we take every step as a beam supported at the wall or within the wall, and the model is quite complicated, but the result is that here at the other side, where it is free, there must be a concentrated power. But what is that concentrated power? So the tension is bigger at the end. And there are various powers working, but it can be done because it is within the step itself. In the sheet theory, this system appears because this concentrated power appears at the end of the sheet. But the result is that we can make such kind of a staircase that it is connected just at the very end. A very thin wall is enough, but this wall should be stabilized between the two supporting systems, between the floor and the ceiling. So if we take a very simple state, it's a joint, a kind of a joint. It's not a console, but when the steps are built on one another, they can be built free. So when we go higher and higher, there the pressure will be bigger and bigger. There will be a kind of pressure, but this pressure is in the middle. So it means that if the step breaks, it won't break at the wall, but somewhere in the middle. So, what if the steps are fixed or built in the wall? So at this time, the steps would like to get apart. So it's not very good if we fix them in a console shape. So what is written in Palladio's book? So the hook should be as wide as a palm, and it means that it is good because the steps don't want to get apart. The technology and function are in connection, and it dictates how these steps can be built even free. Some conclusions. So in case this pressure is not important to have the balance, but it can bear a very big weight. In case of this flying staircase, this pressure is important, and it's very important not to fix it very rigidly into the wall, but more like a joint should function there. And it is proven that it can be built without any supporting system, just free. The next one is about domes. Everybody knows what a dome is. We have lots of relics built once, but there are crackings on them. We want it or not, and they have been there for centuries. Should we do anything about these cracks? They have always done something about it. Committees were created, the committee said something, and then it was just a kind of reassurance. And then they realized that nothing should be done about it. Well, the thickness is different, and there are meridian-like cracks. And they can go up quite high. It can be due to gravitation load, due to the changes in climate. The old masters, architects, builders, try to alter the thickness of the dome. Perhaps it was not a globe, or openings were on the top. There were different attempts. The goal was to eliminate the cracks. But is it possible to build a dome which has no crackings on? On a membrane model, we can examine it. Revolving symmetric, and we can see just the self load of the dome. The question is how thick it should be to eliminate the cracks. Well, we can find such kind of changes in the thickness. Down at the bottom, it is very thick. Yes, there are changes in the thickness. And can we eliminate these thick ones? Because in that way we can build rationally a dome which won't crack. Yes, we can eliminate the upper one. we have to change the so it will be perfect if we change the upper part and the thickness will be the same. But the problem is at the bottom, this thickness at the bottom cannot be eliminated. So it means that perhaps we should build a dome just up to now. We can see somewhere here, the dome is the thinnest somewhere here. We cannot do it. That Levy found the solution in 1888, but well, it got forgotten. So it is possible to build such kind of a dome. Okay, but if I tell what kind of pressure is accepted, how high the dome should be. The singularity will remain, and there are pressures everywhere. I can't do anything about the bottom part, so it will crack. What happens if I eliminate the upper one? We will make a hole. If I keep the thickness at the bottom, then the hole on the top creates a positive effect. And we can make a bigger hole. But if the thickness is the same, then there are tensions, and sooner or later there will be cracks. There are different thickness. Then it was raised where it was supported. Windows were placed. Well, for me, windows are artificial crackings. Positive, are they positive or negative? Yes, they work. So if it works, then with the cracking, it's okay. And then we can see the one with hole on the top. The question is, to thicken, to make a hole on the top, were done to eliminate crackings. But it hasn't been achieved. So the question arises, should a dome be without any crackings? Isn't it accepted? It's natural. We should accept it. Those who design iron concrete ones, they always take crackings into consideration. Well, it was not designed, the cracking was not designed in. What it is a flexible design. It is the deterioration, a kind of deterioration. It is not very visible. Yes, we are faced with it. There are domes which are cracked ones, like the Pantheon, 13, 14 big ones, even your hand could be placed in, or in India, the same size, about the same size of the Pantheon. In case of Pantheon, the thickness is different, but this one is the same thickness. And for 10 meters high are the crackings. The crackings appear always at the bottom. If we make a very simple model, they are very discrete. But if I put it into a model, then we will get a symmetric one. In this case, we will have the upper part, which lies like a membrane shield, but at the bottom there will be the crackings. This is the result. The result is, as we lengthen, as we make it longer, the cracking longer, then the balancing power gets outer and outer. And then after a while, this balance gets out, and then the structure doesn't work. So it means it will work up to this height. And then after a while, the supporting power will go into the thickness. So there is a state where this balancing power is up here, and the structure says, no, I won't stop if it goes on like this. So I will jump into the other one. So a very quick, unstable cracking will appear, and the balance is solved. There are very different tensions on the top part. It is just a speculation, but we don't really often see collapsed domes. But if 4 10-meter crackings are up, and we can see that it is standing because the length of these crackings creates such kind of a balancing effect, which are within the thickness. It's a 3-meter thick dome, and in case of shorter crackings, we don't see longer ones. So the conclusion is that we can examine a cracked dome, that a balanced state, a balanced situation is achieved. But why don't we examine all the domes in this way? On every vaulting, there is a kind of a cracking. Is it negative or is it natural? And it's a natural phenomenon of the vaulting, just like it appears on my body. So, as conclusion, we can say there is a stable stability, a safe stability, even if there are crackings, and the dome will create its own stability, and its own structure can protect itself from collapsion, against collapsion. And there are also there are discrete crackings. In case of Pantheon, there are bigger ones, shorter ones. The longer ones appeared first. And if we see that there are these discrete crackings, we don't have a model to examine all the dome, but I can examine a ring supported by springs, which represents the rigidity of the dome. First, there is just pulling power, and after a while, the ring will have a cracking at one place, second one. I can say, I expect it will appear here. No. It appeared here, close to the first one, and on the same supporting area, there will be one more. So 6 more will appear. They are not symmetric. When looking at it, it's almost, but but they are not symmetric, they are asymmetric. And if it is the same if it starts with 2 crackings. If we raise the load, there will be 2 crackings, but the longest one will be halved. And then if we make a higher load, then these crackings distances will be halved, but after a while these crackings will be shorter and shorter, and we need extra power to create newer crackings. So it means that the rotation symmetric crackings create non-rotating symmetric crackings. So the maximum, there will be maximum 10, 20 crackings on a dome. And I think I will finish my on. So thank you for your attention. And if you have any question, I try to answer.
Thank you very much for this lecture. It seems that he could have continued until the evening, and I have to tell you that I could have listened to it late until the evening. For us, it was a rather unusual area of field for us, and all the problems of monument protection were involved in it. And he represents a point of view which we think we should also represent when we talk about monument protection and restoration. The historicity of the supporting system is indeed one of the most important parts of a building. So based on yesterday's lectures, I'm asking you about this. A structural intervention which we think was not really good on a building, but as for a logic of the time, it was okay. What is your approach? What is the approach of structural designers to these solutions? Just like what you mentioned, considering earthquakes.
Usually the approach is to keep it, but the target is, if it is proven not to be good, then it should be dismantled. But unfortunately, the old interventions will damage the existing, the preserved structure. So the target, the aim is to add something, to change the static model, to make it possible to be dismantled and removed if or when our knowledge develops to the level to realize that it was not a good one.
Actually, I thought of a lot more difficult situation. I'm trying to make it parallel with other things. So there are different principles of restoration. In 1950, for example, there was an era where certain interventions were widely accepted, but now we think that they were wrong, but those interventions represented the thinking and methods of the time. So at least, well, there are things that we have to preserve, even if they are not good.
My opinion is that the first question is it part of the building? Is it considered to be part of the building by the professionals of today, or is it a strange one If we consider it strange and not desirable, then we remove it. And if there are ones which are accepted, then we should preserve it.
Thank you very much. Just a short question. I enjoyed this lecture very much. It's too bad you finished it so early. So did I understand it correctly that from the point of view of supporting systems, the good intervention is if we continue the use of using authentic material, even if it looks more difficult?
Yes, that's my viewpoint as well. But the difficulty is that the modern, no new modern model can be made about old static systems, about old supporting system. The network support was different in the past. This network support was created, which can be calculated. So there are a lot of supporting system nowadays in the modern world, because that was possible to calculate in the old worlds. So we have to make researches how it works and how it was calculated. And nowadays the modern computer technology is not sometimes suitable for it. Very intensive supporting system research has been going on in the past 20 years, but new approaches, new techniques, new parameters had to be introduced to research a ceiling system or a vaulting in an economical way.
Well, as a matter of fact, the challenge for us who deal with monument protection, that we cannot justify the thing based on today's standard. With our eyes today, we try to judge something which was built earlier in the past. This document that you also mentioned, thank you very much for mentioning it. It says that we try to, or we have to try to think over the methodology and the way of thinking of the old times and consider it. I'm referring now to a film which was made in the 1970s. So who can represent that point of view at the university or wherever in the world?
There are some research centers in the world where this aspect, this approach is represented. Now, monument protection doesn't really deal with iron-forced concrete, but now perhaps a movement got started in Italy where they try to preserve the iron-forced concrete structures of Pietro Luigini, and there is also a tender, because time has arrived when the systems of Nervi would like to be pulled down.
It's about the floating chairs. In the inner side of them, what is the... you mentioned that it is a very important thing. What is the operation of this thing? Can it be removed, or do we have to keep it there?
Yes, yes, that stripe
And what about the railing?
can be removed. The rail is just for security systems. Of course, it has some influence on the final utilization, but it's not really important. Well, that band and the bar is not important. To make the sandstone is already suitable.
I'm trying to get back to the floating stairs. I know Attila Szabó, geologist, is the one who you worked with about the model. This Castle Garden Bazaar floating stairs was born, as you mentioned, that you made a model of it, and how important it is not just to think about professional approaches, but together. Different professionals should think about it together. And I'm getting back, or would like to get back to Tamás's example, Mostar. Tamás mentioned yesterday the bridge in Mostar. It has a very special life. They replaced the earlier structure with a steel structure. What do you know about that?
Yes, it's a combination of steel and iron forced structure, concrete structure, but the original shape. And as I remember, local masters were working on the construction. The original material could have been used, but that's another technology. In many cases, they don't take this to build it because there is no builder to make it. It's very difficult to answer because present builders are used to another system and just build, but they don't undertake the task of old structures building.
I'm also asking about the floating stairs as a static question. You mentioned these are not fixed to the wall with a console, but the part in the wall statically works as a twist. It means practically that there should be some sort of movement all the time, just like in the situation of bridges. There is one part is fixed, and the other part is fixed in the other way. So there should be some cracks in the wall if they move, but there are no cracks in the wall. We couldn't see any cracks in the wall.
The movement is very little. The leaning is one at the far end of the step is just 1 millimeter. And if you go into a staircase, you will see that at the wall there is some peeling of the paint. It is, and well, it is not because of the steps, but because they mop or they clean the steps, and there is some liquid going there, and there is some mortar put there, and it allows that little movement. Yes, you can see it, but it is because of the cleaning of the water that gets there.
About the balcony, I'm asking about the console. As the public knows, it is also a console. The horizontal balcony, is it built of stone?
It also always has some kind of a supporting system.
And okay, if we have a dome, we can tell how the second and third crack comes, but how does the first one comes?
The first one will appear at the weakest part of it, where statically it is the weakest, the most unstable. There is just the pulling power. This model doesn't show it. We would need another model which adds the dome as well. So it's very complex. It's not a very bad model. One of our PhD students made experiments and found the same, that one cracking appears, then not too far from it, another one, 2, 4, but there in the experiment we concentrated just up to the top, but here the self-weight was important. So in the experiments the result is the same. So there are different symmetric powers. If we take an iron-forced beam and there is symmetric load, in all the experiments we found asymmetric crackings. It has been mentioned in several studies, but nobody deals with it. It is necessity. There are consequences, of course, if the load is symmetric and there are symmetric damages, and the story is different if there is symmetric load and the damage is asymmetric. There are situations when it is reverse. We are just dealing with one of our PhD students, and we thought that it's always geometry, material, all have their influences, and it gives 10-20% variation. One beam behaves in this way, the other beam behaves the other way, and if we create the same beam from the same material, it very often happens that one behaves this way, the other one behaves the other way. In thermodynamic aspect, it is necessary.